badminton, these are some of my favorite math stories. In this episode, Mathematics is Non-Transitive. We'll explore some situations where a standard piece of common sense does not work. The mathematical property of transitivity is one that we unthinkingly use when we rate products. If I have a top 10 list of favorite things, an assumption that I don't have to clarify is that liking number 1 better than number 2 and liking number 2 better than number 3 also means that I like number 1 better than number 3. This is the transitive property, and even though we often take it for granted, not everything in life is transitive. One little bit of semantics to clear up. In math, the opposite of transitive is non-transitive. Intransitive applies to verbs, and I am intransigent about that. Here's a challenge I've given my classes over the years. These are 6-sided die, standard except for the numberings. The green die has all 3s. The other dice have the following numbers: purple 4 4s and 2 0s, orange 3 5s, 3 1s, blue 2 6s, 4 2s. You and I will pick one of these and then roll them trying to get the higher number. We'll play a best 4 of 7 series. And to be nice, I'll let you choose first and pick the die that you think is the best for this contest. I almost always win. In fact, for a couple of years, I never lost. The secret is that by choosing second, I can guarantee myself an advantage. In particular, I'll win each single roll 2 out of 3 times. In a best of 7 series, this gives me a better than 80% chance of winning. Let's look at some details. When it's purple versus green, purple wins with a 4 out of 6 times, and loses with a 0. So purple beats green 2/3 of the time. Orange versus purple is a little harder, but orange wins with a 5 3 out of 6 times, or with a 1 if purple gets a 0, and this ends up happening 1 out of 6 times, for a total of 4 out of 6. Orange beats purple 2/3 of the time. Blue beats orange with a 6 2 out of 6 times, or a 2 4 out of 6 times matched up with a 1 3 out of 6. Add it all up, you get, guess what? Blue beats orange 2/3 of the time. So blue beats orange, which beats purple, which beats green. Obviously then, blue is the best and would easily beat green, except that it doesn't. Blue wins with a 6 2 out of 6 times and loses with a 2 4 out of 6 times. Green beats blue 2/3 of the time. These dice are non-transitive. There is no ranking of dice from worst to best. Whichever die you choose, I can choose one that wins 2/3 of the time. Now, does this strike you as weird? If you're a sports fan, you may be familiar with cycles like this, where Team A beats Team B beats Team C, and Team C beats Team A. In fact, in the 2024 NFL season, Dallas beat Washington, Washington beat Philadelphia. Does that mean Dallas beats Philadelphia? Not even close. We can usually think of this in terms of upset wins or a good day, bad day, maybe a possible matchup. But the blue die is not having a bad game if it loses to the green die. Blue does not match up well with green. Head-to-head, green is better than blue. But even though purple is better than green, that does not make purple better than blue. A more important example of a non-transitive process occurs in voting theory. Oddly enough, when individual voters rank candidates in a transitive manner, the overall outcome of a vote can be non-transitive. Suppose there are 3 candidates in an election. We'll call them A, B, and C. There are 19 voters total, each of whom ranks the candidates first, second, third. The assumption here is that this is a transitive ranking. That is, if I rank the candidates in the order A, B, C, I prefer A to B, I prefer B to C, and I prefer A to C. In voting, we like to have a majority rules principle, so we'll decide the election by looking at all of the head-to-head matchups. We can do this easily since we have each voter's transitive preference list. Suppose 8 voters rank the candidates in the order A, B, C. 5 voters have the order B, C, A, 3 voters have the order C, A, B, and 3 voters have the order C, B, A. This is a close election. In terms of first place votes, A has 8, B has 5, and C has 6. To see which candidate the voters prefer, we'll look at 2 candidates at a time. Do the voters prefer A to B or vice versa? The first 8 voters have A ranked higher than B. The next 5 voters have B above A. The next 3 have A over B, and the last 3 have B over A. Add it all up, A gets 11 votes and B gets 8. A wins. What about B versus C? Well, the first 8 voters prefer B, the next 5 prefer B, the next 3 prefer C, and the last 3 prefer C. In all, B wins 13 votes to 6. So A beats B and B beats C. We don't really need to check A versus C, do we? Well, we better do so just in case the voting process is non-transitive. A versus C, the first 8 votes go to A, but the rest of them, all 11, go to C. C beats A. That's crazy. Starting with transitive voting preference lists, we end up with a non-transitive result. This non-transitive property was discovered at various points in the 1700s and 1800s by different people trying to determine the best voting method. The Marquis de Condorcet of France wanted the perfect voting method for the new French government after the 1789 revolution. The result A beats B beats C beats A is called a Condorcet cycle after him. This cycle is not the full reason that Condorcet has a statue in Paris near the Notre Dame Cathedral. However, it is the reason I posed next to it. A British mathematician named Charles Dodgson also found cycles thwarting a proposed voting system in the mid-1800s. You might know Dodgson by his pen name of Lewis Carroll, the author of the Alice in Wonderland tales. In Alice in Wonderland, the March Hare says, "You might just as well say that I like what I get is the same thing as I get what I like." This isn't really a Condorcet violation, but it does show how Dodgson played with various mathematical properties, in this case the commutative property, or more accurately the converse fallacy. An end result of the search for the perfect voting system and the inconvenience of Condorcet cycles is called Arrow's impossibility theorem. Given a small number of properties that a good voting system should have, I won't go into them here, but we can talk about them in a different episode. There is no possible voting system with all of the properties. The perfect voting system can't exist. We are so used to ranking items with an unspoken assumption of transitivity. If I like A better than B and B better than C, of course I like A better than C. But the transitive property almost feels like common sense. However, the transitive property is not always true, and one example of a non-transitive situation is at the heart of debates over the best voting system. These little mathematical properties are important.